welcome. Today we have our own host as a speaker as well. So he's going to play double roles for today. Manny is fellow founder of the Cambridge startup for genomic medicine. He is Institute of the curriculum of Manny is very long and I forget all of the names. So he recently organized the first Congress for Genomic Medicine in Madrid, but he's also chief scientist of Cambridge Precision Medicine, and he's a fellow of the International Society for Computational Biology. And his work has always focused on both genetics and genomics. He's also one of the, or the main author of the Cipher, if you've ever used that package. I have, by the way. Thank you very much. And his focus today will be around the importance of ancestry and sex diversity in the genomics datasets and databases, which he is usually lacking, unfortunately. So,
thanks so much, Andy. I appreciate that. That's a nice introduction. So, obviously, organizing a meetup has its perks, doesn't it? But today, I am going to talk about a theme which I feel very, very passionate about, and hopefully I'll be able to share some of that passion with you guys. But before I actually go into the meat of this presentation, I've imposed myself that I'm going to say 3 statements every time now that I do any kind of presentation about the research I'm doing. Because a lot of the research that I'm doing now is coming from underrepresented populations. And I just want to state that I fully respect not just indigenous peoples and their rich traditions, but also I treat them with the utmost sensitivity and acknowledgement, as well as their cultural significance and the heritage of their civilization. And I also strive to honor and ensure that my research upholds the dignity and respect to their own descendants. This is because I do a lot of research on indigenous populations, right now in South America. And I condemned genetic colonialism. For those who don't know what genetic colonialism is, it's basically Western scientists or people from abroad that go and basically exploit the individuals from specific lands without benefit sharing and without really taking into account the cultural context of the place where they take the samples from. So I'm fully committed to ensuring that the benefits of genome research are shared equitably with the communities involved. And I also acknowledge that today, in this age and in this day and age, I can't assume that as a scientist I'm trusted. And I think we all experience the fact that science basically is not as trusted as it used to be. And I recognize, therefore, that there have been historical abuses, and I endeavor to build the bridges through transparency and collaboration, and overall engaging with the public conversation so that the science has the real place that it deserves, which to my mind is probably among the closest to the truth that I've encountered in my life. So I have the privilege of counting or aspiring myself as a scientist, and therefore as such I have the mission to also help in every way I can building trust in science. And now, given this preamble, I'm going to go into the actual sort of meat of my presentation. But I want to start with this publication that came out in 2016, led by Alice Popejoy and Fullerton. It came out in Nature. And this was, in my view, one of those papers that really changed perception in this field of genomics and really precision medicine in general. And what they found is that by analyzing one of the resources that exists at the European Bioinformatics Institute, which is called the GWAS catalog. For those of you who do not know what a GWAS is basically a genetic model, statistical model, that is used to explain variations that are associated with complex diseases. Complex diseases such as type 2 diabetes, breast cancer, prostate cancer, atrial fibrillation, inflammatory bowel disease, and coronary artery disease. So these 6 diseases that I just enumerated are involved in 20% of all deaths in industrialized nations. And so for us, in order to be able to understand the genetic component of genome-wide association studies associated to, and markers associated to these diseases, we use genome-wide association studies. And what she found, after comparing the initial first study, which was conducted by Need and Wunsch, she actually did it in 2016 with a huge number of studies, 2,511 studies, and 35 million samples, as opposed to 1.7 million samples. And what they found is that there is an overwhelming bias of the data that we have, which has been mostly generated using individuals of European ancestry. And so why is this important? Because as we approach the era of artificial intelligence, and we become dependent on these data sets, so the data sets that we have with which to train the data, from which we then apply personalized therapies and treatments, is obviously biased towards the specific characteristics of Europeans, which means that the further ancestrally you are from Europeans, the less precise precision medicine models are going to work. And so there's an issue of not just social justice, but also data equity. And as a consequence, we are also failing not just on diversity, but also we are failing on the promise of precision medicine, because there can't be precision medicine if it's just going to favor the few. And so throughout my last couple of years, I've been heavily involved, first of all, in understanding where are the gaps, because obviously there have been a number of studies, mostly around genome-wide association studies, which were the first sort of quantification of biases that raised the alarms. And since then, there have been more studies. This one was actually developed by Segun Fatumo, who is a close collaborator of mine, and he did a new genome-wide association study quantification of ethnicity. And even though around 2016 we already had that bias being reported, what we found is that actually the diversity continues to so the disparities continue to increase exponentially. And this is mostly because most of the data that is used for genome-wide association studies is based on the UK Biobank, which happens to be mostly white British, and therefore the samples that are used for these models are mostly based on white British. So based on how far your own ancestry is from white British, existing models are going to be as precise or as little precise, depending on how distant your own genetics is from that particular population. And if we actually look at the different countries that have been represented in existing genome-wide association studies, you can clearly see that there are two massive blanks in Africa and in South America, which means that two of the most diverse populations, where there is the greatest richness of diversity in existing populations, are actually uncharacterized. And as a consequence, since all of the models that we have for predicting pathogenicity use low frequency, so if you have a mutation, a pathogenic mutation is more likely to be pathogenic if it's in sort of low frequency. But we have seen that because it's mostly developed in Europeans, that there are some already existing classified pathogenic mutations that, some populations in South America, 20% are carriers, which means that obviously that's not pathogenic because they're happy, they're living around. So it's not just a question that it benefits them. I think it benefits all, because without having the richness and the diversity of the variation that composes the genetic diseases, we will never be able to fully have the actual variants that are contributing to disease. So this GWAS diversity monitor, as you can see, for non-Europeans and non-Asians, there is a representation of less than 3% in existing data sets. So as I said, even though this has been happening since the mid-2010s, actually the proportion of samples from underrepresented populations, it continues to decrease. So these disparities and this lack of data equity is basically increasing. The inequity is increasing. So underrepresentation does not only occur in genome-wide association studies, and this is a study that we actually performed using pharmGKB, which, for those of you, I'm just going to very briefly explain. So pharmacogenomics is the science that, the branch of genomics that basically tells us optimal dosage for any drug based on the genetic variants that the enzymes that metabolize those drugs have. So since every drug, let's say codeine, when you take it, it gets metabolized into morphine, and so depending on the enzyme that metabolizes codeine, the variation, you're going to have different rates of, how can I say, what's the word? Different rates of metabolization. And so if you have certain variations, you might end up having an overdose of morphine. So this is very important, specifically for some underrepresented populations, as we shall see in a moment. So pharmGKB is actually the global resource that basically gathers all existing pharmacogenomic data, so gene-drug reactions. And so thankfully all of the data that they have is fully open source. And as part of my research, we basically quantified, based on individuals and studies that we have data for within pharmGKB, the percentage of existing data that is associated to any of the different biogeographical regions that they have classified here. So American in this case mean Native Americans, Sub-Saharan African, European, East Asian, and Oceanians is actually not you. It's actually indigenous or Oceanians. I understand that we cannot call them Aboriginal now, so we call them Oceanians. So and the sad truth is that when we actually quantify how much underrepresentation exists proportionally to their global share of the population, we see that obviously what we expected, Europeans are the most represented, but also East Asians. But then something that really caught my attention is that proportionally speaking, since Central and South Asian, so we are talking about mostly India, Pakistan, Bangladesh, and maybe Kazakhstan, there are about 2 billion people in the world, and around 2% of existing pharmacogenomic data comes from those populations. That makes them the least well represented. And even though we have a lot less data from Native Americans, because there are only around 62 million people, so their share of the population that compared to the amount that exists in pharmacogenomic studies is not as underrepresented. But one of the main points which we are currently trying to publish is that actually this quantification of underrepresentation based on the actual share of the global population is a very poor measurement, because we know that, for instance, there's more variation in sub-Saharan Africa than the rest of the world combined. Can anyone tell me why that is? Why is there more variation in Africa than the rest of the world combined?
Ancestral population.
You know Homo sapiens, right?
Yeah.
Right. So Homo sapiens happens to have arisen somewhere in East Africa 300,000 years ago. And the first Homo sapiens that came out of Africa was around 80,000 years ago, which means that there have been 220,000 years of evolution of Homo sapiens just in Africa, which makes some of the tribes in Africa, which are neighboring tribes, some of them more different than there could be between Europeans and Asians, for instance. So there's a huge amount of variation, which still remains to be characterized. And the same happens for Latin America and indigenous Americans as well as Oceanians. So this is one of the main, I guess, sort of messages that I want to transmit this evening, is that we don't have proper metrics to be able to identify diversity. Everyone is telling me different definitions of what diversity is, and these definitions continue changing. So I don't know what the solution is, but I'm just saying that currently, if we really want to bridge the gap on what diversity, on the diversity aspect, there has to be some kind of metrics and some kind of standards and some kind of transparency and some kind of statistics sharing, which don't exist as of today. And I don't have the power to change this, but I'm just saying that this is something that perhaps should be considered. I have some other data sets that I have been studying where, it's not just pharmacogenomics either, because, you could argue, we all know that underrepresentation is systemic, right? Well, we all suspect that it's systemic, but as of today, we are not sure exactly what underrepresentation is. So what I try to see, or what I try to demonstrate, that this underrepresentation is actually happening in pretty much every data set that we got, for which there is data for, because there are many other data sets for which, unfortunately, there isn't actually the capacity to be able to assign ancestries to individuals. So that's even worse. I mean, I'm thinking, for instance, dbGaP or any of the other, CleanVar, any of the reference data sets that you can think of. Many of them, they don't have actually information on the ancestry of the individuals from which their findings were derived from. And that's obviously a problem. But for those where there exists, where we, I'm not trying to cherry pick these particular aspects of genomics. I'm just looking where there is some data. So then we also looked where there was data reported, and FDA actually, in the report 2015 to 2019, they do provide the percent of clinical trial participants by ancestry. And the message here is that pretty much, except for a few African-specific diseases such as malaria and some others, very few. The vast majority of the clinical trials are first trained with the Europeans, and then based on that, they sort of transfer to other regions. And then from what you can see here is that, and this is another point I want to mention, is that everyone has different sort of classifications of ancestry. So if I go back here, so you have Sub-Saharan and Near Eastern, and apparently Iran is Near Eastern. I have seen some other places where they actually put Iran as Central Asia. I've also seen some places where the whole of Africa is, so they don't make any difference between, Arab countries or North African countries and Sub-Saharan Africans. So there is a lot of, it's impossible really to properly compare what exists. So there's no interoperability in the way we report or results on diversity are reported. And coming back into pharmacogenomics, so thankfully again, because PharmGKB provides the data, so I want to talk now about this gene, which is called CYP2D6. So CYP2D6, for those who don't know about pharmacogenomics, so this one gene metabolizes 25% of all prescribed drugs that exist. So more than 100 different drugs. My last count from FDA approved drugs is around 400, 500, if I remember. So around 100 are metabolized by this one gene. So if I then measure based on the genetic variation that we know of for this particular gene, and then infer how well the different biogeographical regions are able to metabolize the different drugs that can be metabolized by this, I want to draw your attention to sub-Saharan African, which has a significantly greater percentage of alleles that we know exist for CYP2D6 that we have no idea what effect it has on Africans. And this is actually one of the main reasons why, for instance, in Ethiopia, which has around, so 30% of Ethiopians have a mutation that causes severe adverse reactions. And because they can't genotype the population, they basically banned codeine, which is one of the sort of most common drugs. They are not prescribed in Ethiopia, for instance. And then we also see another, there are many examples. And the reason for giving these examples is because at some point I was telling them, well, so data sets are very biased. And I know that we are all here thinking, yes, we all need to, but then some people could ask, so why should we care? Okay, they are biased, but why should we care? Why this? What does this mean? And there are very, very clear examples, which I'm trying to put forward here, that show how the health of specific populations is being affected, and they're not having equitable access to the benefits of precision medicine that exist. I'm going to give you one example, for instance. So warfarin is the leading drug for anticoagulant, okay? And is among the top 4 drugs leading to hospitalization from adverse drug reactions, not just in South Africa, but everywhere in Africa, okay? And this is because the algorithms that we have for prescribing the optimal dose for warfarin have been trained in Europeans. And we are able to predict really well for Europeans, those that are going to be, ultra metabolizers or poor metabolizers, which could lead to overdose or infradose. But that doesn't work for non-Europeans. So here you have a very clear example from a leading drug that, because we don't have data for these specific populations, they are actually suffering the consequences of not having this data represented. And some of you may have heard of polygenic risk scores. So polygenic risk scores are basically models that assign weights to genetic markers from many genes. And as I said, type 2 diabetes, for instance, may have like 6 million different SNPs contributing very, very tiny things, very, very tiny weights, each of those 6 million SNPs. But if you put them together, if you sum the weights of the contributions of each of these SNPs, you end up having a sort of normal distribution of high-risk individuals. The vast majority of the individuals have an average risk, and then some of them have low risk. And so these models, when we actually train them and compare the precision between Europeans, Americans, South Asians, East Asians, and Africans, you can see that the further you are in terms of ancestral terms from Europe, the less. So if prediction accuracy is 1 for Europeans, then you can see that the further you get, the less accurate these genetic models are for those populations. So here is another example where we see how the benefits of precision medicine is not working for many populations. Unfortunately, it's not just a question of ancestry, it's also a question of sex. Not that sex. Because, for instance, in pharmacogenomics, we know that women experience adverse drug reactions twice as often as men. And a lot of this is because, for instance, women tend to have greater life expectancy, and so they are more likely to require polypharmacy. In other words, when you are at an advanced age, you may have to have more than one medication at the same time. And so there are interactions there that we don't really understand, and that because they are based on models where we don't have the women involved in those models, it happens that they tend to suffer, and they are more likely to have adverse drug reactions because of that. Also, we have that women represent only 38% of participants in drug efficacy and pharmacokinetic studies, even though they are the ones that are statistically most affected. We also know, for instance, that for pregnant women, there are no clinical trials for very obvious reasons, because safety reasons, but we have no data on clinical trials for pregnant women. I think I'm just guessing, this is probably why, sometimes they say, pregnant women don't have this medication or whatever. It's just simply, there isn't any data for that. And so, anyway, another example for chronic pain using opioids, women experience around 50 to 70% increased risk of adverse drug reactions. But there is also underrepresentation in genomics workforce. And we have this paper that came out a few years ago from Eric Green from the NIH, where they basically saying that genomics workforce must become more diverse. And so some of you might have come across this organization, which is the Global Alliance for Genomics and Health. So the Global Alliance for Genomics and Health is an international organization that basically involves the leading genome research institutes, Broad, Sanger, you name it, thousands of them. And so it's the biggest international organization in genomics, and I'm part of the EDI, the Equity, Diversity and Inclusion Committee, and we set out to really understand the proportion of, because by looking at the individuals from the different institutions across the world involved in GA4GH, in the Global Alliance for Genomics and Health, we can have an understanding of the sex breakdown from these institutions. And so we have around thousands of participants where we actually just ask, are you male or female? And as you can see, there's a severe underrepresentation of women, not just at the level of leads, but also at the level of participants. And another bias, actually, is that they're mostly coming from the Anglosphere, so that's Canada, US, British Isles, Australia, and New Zealand. So the vast majority of people come from Anglo countries who are involved in these populations. Although there are some representation for steering committee members that at a leadership sort of level that come from other countries. But this is not the only type of underrepresentation that we found. We also have found underrepresentation in direct-to-consumer genetic testing. And of course, some of you may think that, let's say 23andMe, have you heard of 23andMe? You have heard of, these companies, we're going to give you the Ancestry and so on. And yes, of course, the clinical value, I'm not here to judge the clinical value, but what I do believe is that these companies are a first step for the general public to sort of become acquainted and, if you will, educated about genetics, genomics, and from the point of view of education, I think it's an interesting tool to consider. So one of the things that we decided to do is, because we are geeks, bioinformaticians, and so I actually gave this presentation at this meeting around 2016. And basically what we did at the time, some people, the ones that are geeky like us, you can actually download your genotype, your data from 23andMe. And some people at the time, the ones who were crazy like me, decided to share them in resources. So there are a number of databases, for instance, OpenSNP and the Personal Genomes Project. So we scouted the whole of the internet looking for open access 23andMe genotypes. We curated them, basically checked that the file is not corrupted, that it contains all the data, that there are no duplicates, and so on. And we ended up with a clean data set of around 2,280. And then we just simply perform something called a principal component analysis, which is basically the reduction into 2 dimensions of the variability of genetic differences between individuals. And so as a reference, we use the 1,000 Genomes Project, which contains data from African, Asian, and European. So you can see these data, the Africans here, the Asian and the European. And so when we superimpose the 2,280 genotypes, open access that we found, pretty much 95% were of European origin, according to this. So what this means, and obviously I cannot say, because 23andMe currently has more than 10 million customers, but and also there is a limitation that there might be cultural differences. I don't know if Asians or South Asians are more prone to share their data. Maybe they're not. But assuming that there were no cultural differences, what this is saying to me is that there is a tremendous skew, there's a tremendous imbalance in who's actually accessing this. I mean, it's not surprising because for us maybe spending $200 is not that much, but for the vast majority of people around the world, it's not just the fact that $100 or $200 is a huge amount of money. It's also that even the companies don't supply outside of North America and Europe and perhaps Australia. So they don't even bother sending this. So as a sort of trying to be up to date, so I retrieved this information that has been published by 23andMe, and this is quite recent. I think this is maybe, so this is the most recent published proportion of ancestries that 23andMe have. So I said that there are 10 million, more than 10 million customers, and basically they say that they have around 1.3 million Latinos, 314,000 East Asians, and so on. So even if this is the most sort of accurate, up-to-date, obviously they don't put Europeans because there would be more than 10 million. But they're trying to sort of saying, well, we're trying to do something about it. And I don't blame them because, I think actually the fact that they're already providing this data, good for them, right? But what this all means is that our ability to really stratify and use the data from underrepresented populations is compromised. And even in places like the UK Biobank, where basically around 460,000 of the 500,000 are white British. So there is around 40,000, if my mind doesn't play me tricks, that are non-white British. So 40,000 is, I guess, is there maybe 10,000 Africans, something like that. So and it's actually a reflection. So the UK Biobank is not biased. It's actually a reflection of the proportion of ancestry that existed. When it was started. So in the early 2000s, that was the actual. It was very close to the breakdown of the different ancestries in the UK. But now in the last 20 years, that's completely changed. So that what this means is that, and what you see when people are trying to use UK Biobank data, is that actually they discard non-white British because they don't provide statistical power. And so for many of these analyses, you actually need to have the numbers. And I've done it myself. I'm guilty myself, right? We discard non-white British because they don't provide statistical power. So, the strong get stronger and the weak get weaker. And so, the results continue to be biased. So what are the current barriers and limitations? So why is this, why is it that we are regressing instead of progressing? There are many causes, but we've reported basically that obviously it's money and resources, first of all, right? But then it's also, and this is something which I find quite interesting, that me as a Westerner, we don't think about. It's just we assume that technological advance is good by default. But that's not necessarily the case for different cultures. And we are trying to sort of say, yes, you should have this data because it's going to benefit you. But that's because we are thinking of it from our bias point of view. I think there has to be a much greater dialogue, a much greater engagement with different cultural values, with different views that allow us not to basically sort of be paternalistic, but rather to sort of allow to have this benefit sharing to flourish. And, what recommendations? Well, I mean, and this is what we are doing today. So we are increasing awareness. Of course, it's very easy to say this. I mean, actually to put it in practice is very difficult. But I think, if we are able to at least understand where the problems are, what the biases are, then we can perhaps begin to start at least closing the gap, even if not numerically, at least in terms of awareness. But then there's also the issue of regulatory uncertainty. So we don't know what diversity is. We have no standards for diversity. We don't have metrics. There's no requirements for sharing diversity. The ones that do it, they do it their own way. So there's a lack of transparency, and I'm not blaming people for not doing it. I mean, this is hard, right? This is very hard, and this is a problem. And so I'm just going to basically say that, in terms of research, we've looked at GWAS, but we've also looked at clinical trials, we look at direct-to-consumer, we've also looked at pharmacogenomics. Wherever we look, we find a very severe bias towards Europeans. I'm European myself. It's not that we have said, yes, let's going to, discriminate against other people. No, it's that's where the science was developed, where the money is for research. So, that's why. It's not that, we're trying to sort of say, we should exclude people. And I think what is important, and, I've been told off for saying this because obviously I am basically the wrong sex, the wrong, ancestry, whatever. But I think the issue is that it doesn't just benefit underrepresented populations. This benefits everyone. All right, because there's a lot of errors that exist in public databases simply because we don't have the actual real genetic contributions. And so it's imperative in my mind that we really need to address this. And everyone should have access to the benefits, irrespective of their ancestry, their sex, their wealth. And we need to quantify this, and we're not really getting even near to have any kind of standard. And this is leading to inequities in healthcare outcomes. Hopefully, I've convinced you that there are many problems as a consequence of that. And I'm just going to say thanks to the people I love, and I've been collaborating for many years. I also love you too, but these people as well. And I want to finalize with this sort of article of the International Convention on Economic, Social and Cultural Rights, which was adopted in the 60s by the United Nations. And basically it says that everyone should have the right to enjoy the benefits of scientific progress and its applications. And there has to be respect for freedom, for scientific research, and there are benefits in international collaboration and cooperation in science. So thank you for letting me share today, and that's it. Thank you.